Hello everyone. Today's lecture is going to explain a relatively new class of algorithms within machine learning, which are deep neural networks, and explain how they are useful for molecular data. So as I mentioned, deep learning networks are a very new class of a very new class of machine learning algorithm. So we're going to start off by explaining what they are and what makes them different than conventional machine learning methods. So to really give a very simple example of how they're different, we'll start off with a kind of a cartoon problem of trying to take a picture and identify whether it's a cat or a dog. So if I were to take this picture and build a model using conventional machine learning, what I would do is first try to extract features. I would say measure whether this image has whiskers, count the number of eyes, and count the aspect ratio of the pupil, which in the case of a cat's is very thin compared to dogs. So if I train a machine learning model, it should hopefully have enough information in these feature sets to be able to build a very good discriminator between cats and dogs. In contrast, deep learning models don't require this kind of feature engineering and are built around the idea that you can learn features and models simultaneously. So what this will do is take an image and its constituent values and learn a series of filters that detect patterns in the image. And the interesting thing about deep neural networks is for the fact that they have multiple layers, is they learn progressively more complicated features that describe an image. Say the first layer can detect rods in the image. The second one can take these line features and place them together to form polygons, and then I can stitch those two together to form a pattern that looks a little bit like a cat, which could give me some very good discriminatory power. And of course, neural networks, the models aren't so simple as this. You'll never get as clear of a picture out as this ears and whiskers, but this is actually one of the main ways that neural networks function and how they give such great predictive power. So to get started on explaining how that actually works for materials, we'll dip into a practical example of explaining kind of where my first area of working in deep learning was as a materials engineer, to explain kind of what its key features are and why I use deep learning in so many of my research problems today. And to put that in context, we'll talk about a problem that my PhD research group, Chris Wolverton's group at Northwestern University, had studied for many years, and that is trying to take machine learning algorithms and use them to predict where we can find new crystalline materials. And the route that we explored for this, starting with a paper by Bryce Meredig in 2014, was to build machine learning models that take the composition of a material and predict the so-called formation enthalpy, delta HF. Delta HF is a measure of how much energy is released if I take elements and mix them together to form a compound. And if I can predict that well, I can predict where new compounds should form. And indeed, Bryce was able to identify 8 previously undiscovered compounds using this technique of taking a composition of a model and predicting its stability, or composition of a material and predicting its stability. And he was able to do this with a model that is not all that great. Its errors are about 10% of the typical value of this property. So we asked in a study with some colleagues in Northwestern's electrical engineering and computer science department whether we could do better with deep neural networks. So starting out, we follow the same path that we do for these typical kinds of conventional machine learning models. We went to a database constructed by Chris's group called the OQMD that has, at the time, about 500,000 DFT calculations that link the crystal structure of a material to its stability, which looks a little bit like this when I aggregate them all together. So you'll see a few of these plots during this example, so we'll take a moment to explain them. Each dot on here is a different structure defined both by its composition, the fractions of different elements, and how they're arranged in space. And I can compute, given that 2 bits of information, what its stability would be using a tool called density functional theory. The OQMD has a large number of these calculations with both materials with low energies and some with high, and that gives me a very good training set for machine learning. So what I did is I went through and I sorted this data such that I found what is the lowest energy I could get at each composition, noting that there could be multiple structures, and trying to build up a data set that would map that to its formation enthalpy. Now, another quick word about how to interpret these diagrams. You'll note that there's a line that connects the points on the outer surface of these clusters. It defines a bounding box known as a convex hull. And what this tells us is which materials are stable if we put them in contact with each other, where scandium oxide and scandium will not react with each other because they're connected by this, and that's detectable by the fact they're connected on these lines. In contrast, if I put this compound in contact with scandium, it can actually form a lower energy structure by decomposing from its current structure into a mixture of scandium oxide and scandium. And you'll see why that's important later when we go to validate our models. Once we had this data, we broke from our conventional machine learning approach, which we're going to learn about in our next lecture, of taking the composition of a material, converting it to element fractions, and then extracting from those fractions some features which describe the underlying physics of the problem. And we know that electronegativity has a lot to do with the stability of a material and whether if it's charge balanced or not. In addition, we also throw in a lot of other features that we're not sure if they're important or not, like the maximum melting temperature of these compounds, and that gives us a good place to start with conventional machine learning. Rather, with deep learning, we forwent that last step and relied on the ability for deep learning models to do that representation learning, that going from raw values and finding little features that we can bring together to be able to supplant that need to develop them on your own. What we ended up doing with those conventional just element fractions is training a very simple machine learning model, a multi-layer perceptron model with 16 layers, ReLU activation functions, which is something you could build very easily with Theano or TensorFlow or really any of the major neural network functions or libraries, so nothing fancy here. And what we ended up finding is a simple network with simple features outperformed what we were able to come up with conventional machine learning, even with the benefit of using these physics-inspired features. So what you're seeing here is the performance of a model measured by its mean absolute error as a function of how much data we gave it to train, measured against a holdout set. And what you can see is at around 4,000 points, this deep learning model outperforms both a conventional machine learning random forest trained on the same features, just the element fractions, or the physics-inspired features that I came up with as part of my PhD thesis. And it actually ended up beating us by about 20% in the end. And this is, to me, rather interesting, that we're able to beat the state-of-the-art model with only 4,000 data points, and you could have come up with this without any kind of physical intuition, or stated a bit more controversially, without ever having talked to a materials scientist. So this was a surprising result to me, and it got even more surprising. When I took a deep learning model and I trained it on a data set where I intentionally excluded certain patterns of atoms, like I removed every compound that contained titanium and oxygen, and then predicted what would happen if I exposed titanium and oxygen together. And you can see from my random forest model on one of these convex hull plots, my energies as a function of composition are not just wrong, they're off by about half an electron volt, which is pretty big, but I also get these spurious predictions of where those stable compounds on that convex hull should be. Rather, my deep learning model gets the energies much more accurately and avoids this problem of predicting spurious compounds. And indeed, when I try another problem, of this time excluding an entire quaternary system, my deep learning model does not predict as many spurious compounds, and in fact seems to recognize that manganese can take on multiple charge states, so you get this interesting pattern of compounds being stable in this little band of my ternary system, but not anywhere else, where my conventional machine learning model doesn't do so well. So one question you may be asking is one that we had. How is this possible? So what we did is we devised a technique where we input different materials into our network and then measured what are my features at different layers in the network. So layer 1 is the first layer in the network of how it converts and what sort of filter it's learning, and then layer 2 and layer 8, which is halfway through. And we did this with both pure elements and a select set of binary compounds. And we'll draw out what we ended up seeing here. So the first thing is we noticed is that in my element plot, we ended up finding that these elements were grouped by their column on the periodic table. And you can actually see that they're ordered properly based on their row: hydrogen, helium, sodium, potassium. And this is a PCA plot we use to reduce it to 2 dimensions. So actually the lines in here are meaningful. I'm moving along a direction of different features. But as I see, if I move farther in the network, that this kind of clustering gradually disappears. When I look at the binary compounds, I also see a similar pattern. At first, I can explain the groupings here merely by the groups, or groups meaning columns, on the periodic table, where 1,6 is next to 1,7, which is next to 2,7, which is next to 2,6, which is next to 1,6. So I can explain just by a stepwise difference. But I end up finding in my second layer and onwards that materials that are charge balanced are grouped together. And this is a feature that's emergent from having 2 or more elements in a compound, and in fact seems to give this idea that my network is going from learning element similarity at the first layer and going on to learning more complicated interactions in kind of the same way that in my cartoon example I could go from, say, learning single features like a line in a material to more complicated interactions, like how those lines can be clustered together in a photograph to make something cat-like. And this feature learning ability has a lot of other advantages. I can take it and be able to accelerate my learning on other problems by, say, reusing these features that I've learned on one data set as a starting point for a different problem. My same colleagues from ECS went on to show that you could do this with ElemNet on other materials. Here I'm cutting the accuracy I'm doubling the accuracy on a model by using a transfer learning rather than starting from scratch with ElemNet. Other people have shown how you could do this with taking neural networks trained on kind of general kinds of image classification like the VGG challenge, and use that for labeling micrographs based on their structure. Spheroidite and pearlite are different kinds of steel structures visible at the micron scale. And you could also do kind of clever things like learning from multiple fidelities of the same material property calculated at different levels of accuracy. And that's a paper, oops, I got the year wrong. This one's also 2020. I will note that, as we pointed out in a previous lecture, deep learning isn't a cure-all, but it's still a powerful enough method for the reasons that I've articulated in the specific examples that I've shown you before, and also as illustrated in this benchmarking challenge, actually having the majority of sub-problems being won by some kind of deep learning model. Okay, so from moving on from this motivation, we're going to talk more specifically in the rest of the lecture on how people use deep learning with molecular data in particular. And the ways that I describe this break down into kind of 3 major topics. The first of which is just using deep learning as a normal supervised learning, and this is something we've been doing for over 20 years in the chemoinformatics community, where I just come up with feature vectors as I would normally and pass them through a multi-layered network to learn a very complex nonlinear function. There's also a few groups who use image-based networks of the kind that have shown a lot of promise for things like image classification, segmenting out cancer in cells for self-driving cars, and really taking all of those innovations in image models and simply trying to shoehorn molecular property prediction into using those techniques by, say, rendering a 2D image of a molecule, coloring it based on different properties of each of the molecules, and applying that into as an input into those image-based techniques. A great example of which is the chemception work out of Pacific Northwest National Laboratory. The kind that I'm going to dig in for more on this lecture are ones that are specially designed for dealing with molecular data, and those are message passing networks. So the reason why message passing networks are so useful is they address a issue of molecular fingerprinting. So if I were to look at an example problem of taking this molecule here and trying to learn or find features that differentiate these different atoms in the molecule. Now if I take them and use my radius 0 fingerprints, I can't properly differentiate all three, but if I go to a radius 1, I can come up with 4 features that each match exactly one of my 4 atoms in the molecule. And this is good. It gives me features that describe each of these atoms, but these features aren't perfect. The fact I have to go to this expansion blindly means that for many different kinds of bonding structures or many different types of atoms in a molecule, I'll come up with a very large number of features, which, as you've seen in your homework, you will have to do some pre-processing on in order to achieve good accuracy with a fingerprint-based model. And that's especially true because these features here don't naturally come with some measure of which ones are more similar to others. There's no indication that A and B are closer to each other than C or D, which also makes learning from these features difficult. And while it is certainly possible to learn from not very informative features, as we can see in that image example of how I can predict a cat entirely from the pixel values in the image, we can do a lot better. And the way we can do that, or one way we can do that, is to use message passing functions, where I take my original molecule, which I can represent here as a graph, and I look at the connectivity between different atoms, and I use that to gradually convolve or blend the different properties of neighboring atoms, which just now gives me a set of features that describe each of these atoms uniquely and have some better properties. It's continuous. You note I've got a continuous shade of color here, and that means that my count of features is fixed. I can describe each of these atoms by one feature each, the degree of redness. Additionally, there's actually a measure of similarity now because it shows that D is the least similar from A based on this feature. And this I can generalize into describing it as 2 different functions. I have a so-called message function, which I can take my neighbors and the type of bonds and use that to define something that describes the environment. And then I can have an update function which takes that message and uses it to update. And you'll note here these colors kind of follow the pattern of how I express my convolutional learning. The trick with message passing neural networks is that neural networks are very good at learning these kind of arbitrary functions. So I can use neural networks to learn good message passing functions that create features that are actually relevant to a particular problem of interest. So going on from this cartoon picture, there's been a lot of work on actually generalizing these notions of message passing networks as mathematical functions. One good paper to read about this came out of Google about 4 years ago by Gilmer and others, where they express all message passing networks as a combination of three functions. Those so-called message functions that go over, again, each of an atom's neighbors and create some message based on the types of the atoms and what they're bonded by. An update function which updates the value of an atom's properties given that message and its previous value. And then finally a readout network that takes all of the values of each of the atoms in a graph and uses that to produce some property. And the very interesting about this, as highlighted well by Gilmer, is that you can take many existing kinds of networks that have been shown for working with molecular data, and you can realize that they're all actually the same under the hood. That whether it's a graph convolutional approach or MPNNS, which introduces this notion of also having a state of features that describe the entire molecule, not just an edge or a vertex, which is a bond or an atom, that they all follow this general pattern of different ways of defining those message, update, or readout functions. Now, one of these I'll dive into a little more detail about is SchNet. So SchNet is based on a concept that is actually very well studied in the computer vision machine learning, is that convolutional neural networks are fantastic. By learning features that look like this, which I take over an image, apply to a certain block of it, measure how much that image responds to this feature or that particular region of the image, and that can give me a very good way of, say, identifying which parts of an image are cancerous or which parts of a viewpoint out of a car's self-driving camera or actually vehicles or pedestrians or bicycles. The problem is of taking these techniques whole cloth and using them on atoms is that atoms aren't pixels. They are discrete points within a space, and you can't really break a molecule down into pixels and hope to capture all of the information. So what they've come up with is this notion of continuous convolutions, where I can take an atom's environment, I can apply this continuous filter as a function of each atom's distance from the center and its current values. And this actually mimics this notion of taking a single pixel, applying a filter to all the pixels that neighbor it, and being able to determine, say, a new value. And this also can be formalized as a message function, where I take all of my neighboring atoms, I use them to compose a message, which in SchNet I then add to the previous values for each of those pixels, in our case, atoms. And that gives me a new set, and I can repeat this throughout the network, and that gives me a convolutional neural network that follows this message passing function, where again, messages are determined by applying this continuous filter based on the distances of each neighboring atom multiplied by the properties of those neighboring atoms, and using that update function to take the old properties and update them to new ones. All right, so this wraps up our lecture portion of our discussion of neural networks, and hopefully I've been able to convince you that deep learning has an advantage of being able to learn from sparse features like the atomic fractions of a material rather than physics-inspired features, and the fact that you can learn very complex models with these deep neural networks means you can achieve high accuracy, and the notion that it learns features means that you can apply those features and use them as a way of starting another problem with a method called transfer learning. The way that this notion of neural networks is commonly applied within the molecular literature is through the notion of message passing networks, where in effect I'm automatically learning fingerprints for each molecule, with each atom within a molecule, using a combination of these message and update steps, and then applying a readout function that takes all of those molecular features, all those atomic features, and gives them a single feature for the entire molecule. So what we're going to do next, these will be posted on our course GitHub, is how I can take these individual types of messages or individual types of functions and express them in TensorFlow and build a neural network based on graph data.